I don't know if you picked up on yesterday, these are all going to be solved between 0 and 2 pi. When you're solving between 0 and 2 pi, that means the idea of the specific parameters for sine or cosine, all that's kind of out the window. The easiest thing to do is just figure out where is it positive, negative, and just plot the first one, and then rotate it around using the reference angles to find the secondary angles, if there are. Okay. So in this case here, subtract 4. Excuse me. And then divide by 2. And now that means cotangent of theta is 0. Well, cotangent is a reciprocal function, isn't it? What's the reciprocal of cotangent? Tangent. What's the reciprocal of 0? Undefined. Very good. So this means that this is the same as 1 over 0 for the. So what angle has a tangent? Oh, you're right the other way. Sorry. That means the exact same thing. That's what you're looking for. Where is tangent undefined? Well, if you remember, tangent being the one that you have, tangent is y over x. So that means that y has to be 0. Well, where's y 0? At 90. And, well, not 180, 270. So you're at pi over 2 and 3 pi over 2. That's where tangent is undefined. Okay? That's where tangent is undefined. Is that okay? Yes, ma'am. Oh, I did mine wrong. I just realized I wrote down. Yes, ma'am. Did I write that? No, because where is tangent because it's where is tangent undefined. Did I say? Did I say? So we're at. Did I say where y was 1? I meant where x is 1. I'm sorry. Yeah, you're right. Because I knew tangent. I knew it's up here because when I graph it, I always at pi over 2. I go through it. So I apologize. It's early. I might answer up because I actually wrote it as 0 factor reciprocal. Silly Murphy. Are we okay on those then on that first page? Okay. On the second page, we had numbers, guys. We had 10 and 11. Sure. We'll look at number 10. Now, when you see that you have, think of this as variables on both sides of the equation. When you have variables on both sides of the equation, what you would do is always pick on the little guy. So, would you pick on the -1 cosecant or the -7 cosecant? Who's the little guy? Yeah. Think of it this way. If this was -x equals -3 minus 7x, what would you move? I would move that -7 over by adding 7x. Okay. And I do the same thing. I'm treating these remember, the cosecant of theta, bless you, is kind of your unknown. All right. So I'm working out of there. So I'm going to add 7 cosecant. So cosecant what angle has a sine of -2? No, very good. And that's it. This is another undefined problem. Once you get to here, you know that your next step would be what angle has a sine value of -2. And if you recognize that right here, just go, nope. Okay? Nope. I literally, when I did I did all my stuff yesterday, I literally wrote down the word nope. And then number 11. What? CJ, all right? Huh? Oh, it's always my fault. Uh-huh. I don't know, somebody that probably didn't do all their homework. I mean, okay, but okay. Anyway, once again, I'm going to go ahead and treat this like I would with variables on both sides. I have a negative 2 secant and a positive 1 t secant, or 1 secant. I can talk again. So again, I'm going to add 2 secant over. At the same time, I'm going to add the 2 to the other side. So what's going to happen here is I'm going to get 3 equals 3 secant of theta, which means I get secant theta is 1. Everybody okay that I rewrite things going to the left? Bless you. Going back to the left, is that all right? Just flipping it. So secant is the inverse of what? Cosine. I don't know why you guys keep using calculators. You're not going to get one. These are played a bunch of them. No, you're not going to get one, right? I'm just reminding you. I didn't know if you were trying to figure stuff out with calculator. So this is the same thing as cosine. So where is cosine? Cosine, is cosine your x or your y value? Your x value. So that means on my quadrantals, I have to figure out where x is equal to positive 1. There. Which the answer is 0. Okay, 0. Cosine is equal to 1. Or the angle that has a cosine of 1 is at 0. (11, 15, and 16. 16? That's a good one. I like that one. Okay? Now this is a good one because this one you still have to solve for x like you would normally. And this is going to be one that you don't remember how we talked about yesterday that sometimes when you take square roots you would have to rationalize. This is an example where you don't need to rationalize because it's easier to fit it into the circle to understand where things get placed. So is everybody okay by me doing this, that it's going to be cosine squared, or cosine of x will equal plus or minus 1 over root 2? Divide by 4, take the square root. 1 over 2. I'm sorry, I was getting ahead of myself. How about 1 over 2? Is that better? I was thinking I just took the square root and blah, blah, blah. All right. So now that means what angle has a cosine value of either plus or minus 1/2? So when you think about it, and I kind of noticed some of you guys are drawing these out. This is the main idea, because if anything that we do, trig is so unbelievably visual. And it's so easy for us to quickly draw a 30, 60, 90 or 45, 45, 90, and then utilize that reference angle, rotate around, be able to place it through. So cosine being a positive 1/2 means that my adjacent is the 1, my root 3 is opposite, so that means that's a 60 degree. Okay? It being plus minus, which means it's going to be every angle in all 4 quadrants that has a reference angle of 60, or pi over 3. So if I move it around with pi over 3 is my angle in the first quadrant. Having a pi over 3 reference angle in the second quadrant gives me a terminal side angle of 2 pi over 3. If I drop down, bless you, if I drop down a third from a whole, I'm adding 1/3 to a whole gives me 4 pi over 3. And then lastly, if I'm at 2 pi, 6 over 3, I move down a third, I'm at, bless you. And those are my 4 possible solutions. Okay. What else on that page 3 do you want to look at? I think we did what, 15? 15 is very similar. I think that's what I was looking at when I did the root 2. 15 is very similar with that. What was the other one? 11? Did you figure out 11 okay? You have to do this first to make anything work. Everybody do that first? I think we did one like that in class yesterday, so we had somewhat of a similar example. So your first rule here is to do what? Take out a cosine, very good. Factor out a cosine. And that'll give us cosine of x is 0, and then 2 cosine x plus 1 is 0. You just have to solve those independently, and I'm sure at this point, those two should be okay to find rather quickly, because I think, in case you haven't noticed, there's only so many answers you're going to be able to get. And a lot of times, even though the equations look different as they start out, your solutions wind up being very similar to ones you've already done. So what angle had a cosine of 0? Oh, that was at, 1 was here, so that's at 90. And at 270, so this was pi over 2. We just did the 1/2, but this is the negative 1/2. So negative 1/2, well, 1/2 was a pi over 3, but it being negative had to go second quadrant. So it was 2 pi over 3, and then 5 pi over 3. What's that? Yes, you're right. I'm sorry. I was thinking sine. I was thinking sine coming around. Yeah, it's 2 pi over 3, and then 4 pi over 3. It's all students take calculus. Yeah. This is what happens when you don't drive. You try to use your brain. Oh, Mackie. How's your brother doing? I haven't heard about him in a while. Nice. Glad to hear it. Well, tell him I said hello. Thanks. Okay. I don't know. And then the last page, numbers 5 and 10. 5. Oh, I love it. 5 is great. You know why I wanted to put this one on here? Because I wanted to show you something new. Because what fun is that? So here's this thing. Since math people are already a bunch of morons, more so than normal, what we've decided to do as mathematicians and things, we decided to just start making stuff up. In case you didn't know that, it's a whole imaginary number crap and all that. It's just imaginary. Just think about it. Don't tell anybody. So what we like to do sometimes is we like to take the overly complicated looking something and make it look easier. For example, what if I did this? I'm going to do let u equal cotangent of x. All right. If I do that, everywhere I see a cotangent, I'm going to put the letter u. Isn't that just a generic factoring problem now? Yeah. What times what is negative 30? You add together to get negative 1.
Oh, yeah.
Negative. Well, it would be How about -6 and pi? You get the -1 in the middle. See, I can do that because remember the rule for factoring. Since we're going down, our degrees are cut in half. I can do this little trick. Refactor it like we did before. So I can split my middle term out to being 2u to the 4th minus 6u squared plus 5u squared minus 15 is 0. This is a problem that we did back with quadratics. Okay. Now, since I have 4 terms, we would factor it via grouping. Okay. So when I go to group this, what's my GCF of those first 2 terms? Okay. So then I'm left with a u squared minus 3. What's my GCF between the 5u squared and the -15? 5. So I factor out 5, and I have the same thing, u squared minus 3. Be okay with that? Are those 2 things in the parentheses the same thing? All right, write it down, and what's left? Now I have 2 terms that I can set equal to 0, don't I? Okay, so I have u squared minus 3 equals 0, and 2u squared plus 5 is 0. But what did u stand for? Tangent. And I'm back to where we can go. What that process is called, it's called U substitution. When you have something that looks like crap and you're not sure what to do, but they kind of have the same thing involved, you throw a U in it because it made it look cleaner. You will use this little trick of U substitution pretty regularly with weird stuff like this, or there's a few times in pre-calc that we'll do it, and then there's a lot of times in calculus that you'll do it when you're taking derivatives and integrals. It's a very, very common thing. This is the first, I don't know if we did this at all first semester. Did we do one of them like that? I think we, yeah, that might have been about the only time we've seen this. So this is the only other time that really kind of shows up of being any use. Did you need to use it? No, I mean, you were saying that this is what you did. You factored it out that way. You just get the cotangents. And that's fine. That's absolutely, it just looked a lot messier. So here, I just go through the process now. I add 3. I have cotangent squared x is 3. Cotangent squared x is the same thing as saying tangent squared x of 1/3. And then I take the square root. So I have tangent of x is equal to the plus minus 1 over square root 3. You okay with that? That just means what angle has a tangent of plus or minus root 3. Move this up here. So your opposite is the 1, you're adjacent to root 3, which means you're at a 30-degree angle. So this is going to be all of your pi over 6's all the way around. So you have pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. That gets me there. So far, so good? Okay, other part. The other part is terrible. Watch what happens, though. You subtract 5, divide by 2, you get cotangent squared x equals -5/2. Can't do anything about that now. And you're right. Because you can't take the square root of a negative. We don't have, hey, I hate to break it to you, we're not going to do imaginary trig functions.
Oh no.
Gotta save something for pre-calc. You remember this? Remember when we wrote stuff out? It was like 3 plus 2i. That was like an imaginary form, a plus bi, and stuff like that. Well, there's a trig form of that. Also, remember we did this? Just because it's fun. What's the cube root of 8? 2, okay. Did you know that there's actually 3 answers to that? Oh, I love that sometimes. We're running out of time. All right, I gotta give you some problems to do. Huh. So, page 1 here, let's do these. Since you've done these, let's do 7, 8, and 11, 12. Not on page 1. Oh, page 2, sorry. 12, 14, 15, and 16. And then we'll worry about, we'll do general solution. We'll get to general solutions tomorrow. Okay? They're really not. It's basically, when you're talking about general solution, if you have a solution here, let's say it's at pi over 6, and the other one is at 5 pi over 6, how long does it take you to get from here? Is the distance from here to here the same as the distance from here to here? So your general solution would be, how long does it take you to get back to here? Every time it takes you 2 pi to get all the way back to where you started. So your general solution would be pi over 6 plus 2 pi n. Every revolution you go around, you went at the same spot. And this would also be, it depends on how it's asked the question. You do all the work the same, how you write your solution. So anything that I post tomorrow for homework-wise, set it up the same way as you did before. Then when we talk about general, you'll be like, oh, okay.